Welcome to MLAC online tutorial, and before us today we'll be looking at the theorems in circle geometry. And the essence of this video is for us to be conversant with the following basic theorems and concepts in circle theorem. Alright, we'll be looking at about 9 theorems in circle geometry in this video. Alright, now look down for number 1, and it says a straight line from the center of a circle that bisects a chord is at right angle to the chord. Alright, first of all, what you probably need to understand a chord. Now, a chord is just a line that cuts across the circumference of a circle. So this line here is what we call the chord. Okay, this is the chord. It starts here from the one end of the circumference and end at the other end of the circumference. Now, but when a straight line like this passes through the center of the circle, now at this point, if it actually passes here like this, at this point it is not a chord, it is the diameter. It is a diameter. Alright, so having said that, this is the chord. So when it bisects, now when a straight line from the center of the circle, this is a straight line that bisects, and bisect means dividing a line equally to two equal parts. So this line bisects a chord, so which means is at right angle to the chord. So when this line from the center of the circle bisects a chord, automatically here becomes 90, here becomes 90 degree, and this line from here to here is the same. So we can now say that line AB equals, line AM equals MB. Okay, all right, so this is the illustration to this theorem. All right, now let's move to number 2. Now, yes, for number 2, and it says the angle which an arc subtends at the center of a circle is twice that which the same arc subtends at any other point on the circumference. All right, here where we have a case, here we have case 1, case 2, case 3, and case 4. All right, now which means you could actually see these cases. It actually still the same thing. You could see this diagram, you could see this diagram, you could see this diagram, and you could see this diagram. All are the same thing. All right, now here's the arc AB. Here's another arc AB. Now here's another one AB, and here is another one A and B. All right, so this arc here, this is another arc. Now another arc, another arc. Now all this arc subtends at the center of the circle. Now here is the center B. B here is the center. B here is the center for this arc, and B here is the center for this arc. And what does this imply? It means that B equals to 2A for each of these cases here. So here we are told that the angle which an arc subtends at the center, so here is the angle that is being subtends at the center of the circle, is equals to twice that which is the same, that which the same arc subtends at any other part on the circumference. Okay, so this is the same arc which subtends at B. Okay, now is twice the angle subtends at the circumference. Now you can see that this A meets at the circumference. Now this A meets at the circumference. This A meets at the circumference. And this A also meets at the circumference. So this law applies to each of this case. Okay, all right. So now that we've understand this, the first one also we've got to understand that. All right, now let's move to the third theorem of the circle geometry. Now let's look at the third theorem of circle geometry, and it says angles in the same segment are equal, or angles subtended on the circumference by the same arc are equal. All right, this is for case 1 and this is case 2. All right, either of this diagram is applied to this rule, or this rule is applied to it rather. Now, and what does this? Now here's the arc AB. Here's another arc AB. Now, which means this same arc now subtends this angle here at this circumference. This same arc subtends this angle at this particular part. Now you can see that both B and A has the same arc. Now from here also we can see that here is the arc that subtends B and subtends A. Okay, all right, no, sorry, this is the arc here rather, A and B. So this arc here now subtends B and A. Now you can see that with this arc, this angle is formed. With the same arc, this angle is formed. All right, so it then implies that B equals A for each case. Okay, that B is equals A for each case, and therefore also when we talk about the same segment here, now we can see from this arc here, now we know that a segment is just a line that divides the circle into two parts. So, and we know that we have the major circle, the major segment and the minor segment. Now looking at this also, we can see this is the first segment, this is the second, this is the first, and this is the second. This could be the first, second, this could be first. Now you can see that this part, this angle, these two angles are in the same segment. Now this also are in the same segment. So to that effect, A, B are equal. Are equal. All right. Now let's look at the third theorem. But I guess also there's also another diagram that will that also gives this law. Now let me get that. Okay, looking at this also, let us make this C and let us make this also C. It also still implies that B equals to A and equals to what? C, because every one of them are in the same segment. All right, now let's move to theorem 4. Now here's theorem 4, and it says the angle in a semicircle is a right angle, or the angle which a diameter subtends at the circumference is 90 degrees. Now here is the center of the circle. As long as this line passes through the center of the circle, Now whatever angle that subtends at the circumference is 90 degrees, right? It would also be this way. This also 90 degrees. It could be this. (90°). It would also be this. So let me say this is okay. 90, 90, 90, and 90. As long as the line or the base of the triangle is the diameter of the circle, then each of these angles subtended at the circumference is 90 degrees. Okay, now let's move to theorem 5. All right, now for case 5, or rather for theorem 5. Now the opposite angles of a cyclic quadrilateral are supplementary. And when we say supplementary, it means the angles involved must be equal to 180, or the opposite angles of a cyclic quadrilateral summed up to 180. Now this is a quadrilateral in a circle. That is what made it what a cyclic quadrilateral. Now a quadrilateral has 4 sides, right? Now enclosed in a circle is what we call what a quadrilateral. Actually, quad means 4. Okay, now from here, now from the law, it says that opposite angle are supplementary. Now which means you can see this A, B, C, and D. Now actually why I write A and B, because they are opposite. So here this is opposite to this, and these two are opposite. Now these two are opposite, and these two are opposite. Now according to the law, it implies that AB plus B equals 180, and C plus D equals 180. Okay, I believe that is clear. All right, so in this case also, A plus B equals 180 degree, and this A, B, this is C. So C plus D equals 180. All right, so when you see cases like this, it is actually theorem 5 that applies to it. As long as either of this line doesn't pass, either of this line is not a diameter. All right, so this plus this, the opposite angle equals 180. The opposite angle here equals 180. The opposite angle here is 180. Opposite angle here is what? 180. And also that makes them what? Supplementary angle. All right, now let's move to theorem 6. Now for theorem 6, and it says the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. Now the question is, what is the exterior angle? Now this is the exterior angle, and this is what? The interior angle. Okay, and it definitely means that A equals to B, or B equals to what? A. All right, from theorem 5 we said something that opposite opposite angle of a cyclic quadrilateral are supplementary, or sum up to become 180. We could also still prove that, we know that angle on a straight line is 180, right? So if we say 180 minus, so here is 180 minus B. Okay, and you can also from theorem 5 we can say 180 minus B now plus A equals 180, which is opposite angle of a cyclic quadrilateral are supplementary, or equals to what? 180. Now if you look at this, so from here now, let us from here we can now probably see 180 here, 180 minus b, okay, plus a equals 180. And from this now we can actually still prove that b equals to a. All right, so and that also will satisfy that so which is here, let us probably subtract both sides by this. So here we have 180 minus b now plus a equals 180. Okay, so right here we can now say subtract both sides, or okay, subtract 180 from both sides. 180 minus 180 minus b plus a equals 180 minus 180. So here we have minus b plus a equals 0. So adding adding b to both sides, so I have minus b plus a equals 0 plus b. So here we have that a equals what? B. All right, so these are also proof that the external exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. Let's move to theorem 7. Now for theorem 7, and it says the angle which a chord makes with a tangent in one segment of a circle is equal to the angle subtended by the same chord in the other segment. All right, now let us define this segment and the chord. Now here is the chord. Now actually a chord is a line that divides this a circle into two segments. Now here is the first segment and here is the second segment. Okay, now this angle now subtends this angle with a tangent, and a tangent is a line that touches the circumference of a circle. It could be here, it could be anywhere, but outside that touches the circumference of the circle. So here now it also will probably imply here now that this is equals to this, right? And x here is equals to b. All right, so the angle which a chord makes with a tangent, now this angle in one segment of a circle is equal to the angle subtended by the same chord in the other segment. Now this is one of the segments. Now subtend this angle at the other segment. Now this angle at this segment now subtends this is equal to this angle at the other segment. Okay, now you can see that this is also an arc. This is also an arc. All right, now this angle here, this is another arc that subtends this angle, another arc that subtends this angle. So this angle here is equals to this angle being subtended by this arc, and this angle is equals to this angle being subtended by this other chord. Sorry, not arc, chord I mean to say. All right, let's move to theorem 8. So before we go, here we have that x equals to b and a equals to y. Okay, all right, then let's move to theorem 8. So theorem 8 says a tangent to a circle, this is a tangent, is perpendicular to the radius drawn to its point of contact. Sorry, this should be contact. Contact. Okay. All right. So from here now, what does this law implies? Now the tangent, this is the tangent of a circle, is perpendicular to the radius. Now here's the radius. From here is the radius. Now this also implies that A equals what? 90 degree. Now this tangent could be somewhere around here. It could be somewhere around here. It could also be somewhere around here. So as long as this radius meets all these angles are 90 degrees. Okay, so that is the theorem for 8 rather. Okay, that the tangent to a circle is perpendicular to the radius. As long as this tangent is perpendicular to each of these radius, then the angle being subtended by that radius to the tangent is 90 degree. All right, let's move to theorem 9, which happens to be the last one. All right, for theorem 9, it says the tangents to a circle from any external point, are equal in length. Now here is that external point C, now that runs through and meets the circumference of a circle. So this is the tangent. As long as this point here, the tangent cut across the circumference of a circle, it implies that AC, the length of AC now equals BC. So irrespective of the points at which this external these tangents are coming from, they are all the same. Probably if it's coming from here, and let me see here again, sorry, so from here to here is equals to from here to this part. Okay, so it could be from anywhere. Let me say this is D, let me say this is D, E, and F. So here DE equals DF. Okay, all right, so this is the last theorem for circle geometry. If you love what I've just done, please subscribe to my YouTube channel and ensure you click on the notification button to be notified of all my videos in mathematics, chemistry, and physics. And in subsequent videos, I will be looking at how to use this theorem to solve problems in circle geometry. Thank you and God bless you.